Okay, so here we know that there's 114 grams of um, octane equal to 1 mole of octane. Okay, so units here cancel out, so I'm going from grams of octane to moles of octane. Now I need to look at for my molar ratio. So here I know for every 2 moles of octane, here 2 moles of octane. Here, so the units for moles cancels out, and then that's equal to 2 moles. Oh, sorry, not 2. It's actually 25. So 25 moles of O2. Okay, so units cancel out there. I'm left with moles of O2. And now the last step is to find the mass of O2, so that's easy enough. So there's 2 atoms there, so 2 times molar mass, which is 16, so that's 32 grams per mole. Alright, so I have 1 mole of O2, and that weighs 32 grams. Okay. Alright, so now I need to do the math here. So I'm multiplying 702 times 1 times 25 times 32. And when I do that, I get 561,600 over 1 times 114 times 2 times 1. And that is 228. So when I divide, if you want to do all this in one step in your calculator, you're certainly welcome to do that. I recommend you do it step by step like I'm doing it, because what seems to be the problem with most students, they forget to put in their parentheses, and you have to sort of account for order of operations in that case. And so you end up with something a little bit different than what you should. So make sure if you are putting it all in the calculator at one time that you're using the correct parentheses in order for the math to work out correctly. All right, so here we have in our calculator we get 2,463.16, and that's grams of O2. And so looking at our starting units here, we have 3 sig figs. So we'll do 2,460 grams of O2. Okay. Okay, so talking about stoichiometry here, it says examples 4.8 and 4.10 illustrate just a few instances of reaction stoichiometry calculations. There are numerous variations of the beginning and the ending of computational steps are possible depending on what particular quantities are provided and sought, volume, solution concentration, and so forth. All these calculations share a common essential component, the use of stoichiometric factors derived from balanced chemical equations. And so we saw that. We were given information that could vary, that we're starting out with a balanced chemical equation in order to do the calculations, and then also having to derive molar masses of different compounds. And so here is sort of a flow chart depicting all of the possibilities, and very similar to what I showed you guys earlier. And so we're starting with the mass of a substance going to the mass of something else, using going from mass to moles using molar mass, moles of A and moles of B, using my molar ratio, and they're referring to that as a stoichiometric factor, and then moles of B to mass of B, using molar mass again. And so again, you can branch off here in different places. If you're wanting molecules, you would use Avogadro's number here once you have the moles of the substance. If they wanted volume, you would and you'd have to start out with moles and convert moles to volume using molarity. Molarity, remember, is moles of solute per liter of solution. And if you wanted to go from mass to volume, you have the density of the substance, you could do that as well. And so you see that on both sides. All right, so your textbook talks about some of the chemistry that happens with airbags, and we know airbags are designed to inflate very quickly, and that happens because there is a chemical reaction. And normally we end up doing an airbag lab. This semester we actually moved it to next semester because we're going to talk about stoichiometry of gases next semester at the beginning. It's usually also put in the first semester, so we're moving things around a bit. But and that lab is kind of neat because you make your own little airbag using a Ziploc bag, and baking soda and hydrochloric acid. So you see that quick reaction, and it's a very quick reaction, and ends up blowing up your airbag because carbon dioxide gas is produced. So anyways, we get to look forward to that next semester. So our next section here is reaction yields, explaining the concepts of theoretical yield and limiting reactants and reagents. So this is sort of just an extension of stoichiometry. Deriving theoretical yield from a reaction or specific conditions. You guys had to calculate theoretical, or actually percent yield in the lab the other day. And this is very useful for experimental purposes. And so what we've done so far is we sort of assumed certain things in our previous reaction. For example, when we started out with, let me go back here. When we started out with a certain mass of propane, for example, if we wanted to find the mass of a product, we assumed we had enough of the other reactant. So actually this is a better example here. We're starting out with so many moles of propane. We're wanting to know how many molecules of carbon dioxide are produced. We assumed we had enough O2, okay? But we don't necessarily always, that's not always the case in reality, okay? So we're going to learn to actually, you have to look at both reactants in order to figure out how much products you can make. You have to have enough of both. And so we're going to look at that, and that's called limiting reactants or reagents. All right, so reaction yields the relative amounts of reactants and products represented in the balanced chemical equation are often referred to as stoichiometric amounts. Okay, I referred to them earlier as molar ratios. Okay, whatever you want to use is fine. Just remember that those words are interchangeable. They mean the same things. All the exercises in the preceding module involved stoichiometric amounts of reactants. In more realistic situations, reactants are not present in stoichiometric amounts, meaning that we assumed that we had enough of the other reactant, when in fact it's possible that, for example, in this calculation, our whole assumption is we had enough O2 to produce this amount of CO2. Okay, they gave us the moles of propane we started out with. We figured out how many molecules of CO2 we made, but again, we assumed we had enough O2. All right, so here we have an example. Consider making grilled cheese sandwiches. 1 slice of cheese is what you need, and you need also 2 slices of bread to make 1 sandwich. If you're provided with 28 slices of bread and 11 slices of cheese, one may prepare 11 sandwiches per the provided recipe. All the provided cheese would be used, and 6 slices of bread would be left over. Okay, so we need to learn the two concepts here. All right, what is a limiting reactant and what is an excess reactant? All right, so the number of sandwiches prepared has been limited by the number of cheese slices, right? Cheese was a limiting reactant because basically I used all the cheese and I couldn't make up any more cheese sandwiches. So the limiting reactant by definition will always be entirely consumed. Thus the amount of product that may be generated is limited because you're basically running out of an ingredient. Okay, in chemistry, you're running out of a reactant. The bread slices have been provided in excess. The bread is the excess reactant or reagent. Okay, why is it excess? Because you have leftover bread. It's just sitting around. Okay, so here's a nice picture showing you what constitutes a cheese sandwich. Okay, and then you have 28 slices of bread, 11 slices of cheese. You make 11 sandwiches, and guess what? You have leftover bread. So our cheese is our limiting ingredient, and our bread is our excess ingredient. Now consider a chemical process. So here we have hydrogen gas and chlorine gas producing hydrochloric acid gas. Imagine combining 3 moles of hydrogen and 2 moles of chlorine. One approach for determining the limiting reactant involves comparing the amount of products expected for the complete reaction of each reactant. The reactant yielding the lesser amount of the product is the limiting reactant. Alright, so when I'm given certain masses or moles of each reactant, we have to figure out how much we can make of HCl, okay, using, assuming we have excess of one or the other. What's going to happen is you're going to get 2 different values. One's going to be lower than the other, okay, so that's what they did here. So here, if we're starting out with 3 moles of hydrogen gas, and look at our molar ratio here, for every 1 mole of hydrogen gas, 2 moles of hydrochloric acid are produced. I can produce 6 moles of hydrochloric acid. If I'm starting out with 2 moles of Cl2, for every 1 mole of CO2, I can produce 2 moles of HCl. I can produce 4 moles total of HCl. So how much HCl can I really produce? Well, I have 3 moles. I'm starting out with 3 moles of H2, and I'm starting out with 2 moles of Cl2. But obviously, I can't make 6 moles of HCl because I don't have enough Cl2. Okay, according to the amount of Cl2 I have, I can only make 4 moles of HCl. Just like I couldn't make any more sandwiches more than 11, because I only had 11 slices of cheese. Okay, I ran out of cheese, and so same idea here. I ran out of Cl2. I can't make 6 moles. I can only make 4. So notice that with limiting reactant problems, they're going to give you the number of moles or the mass for each reactant. You convert it to one product. In this case, there was only one product to convert it to, but when there's 2 products, it doesn't matter which one you convert it to, as long as you're converting it to the same product each time. Okay, so the Cl2 will be, or the Cl will be consumed once 4 moles of HCl are produced. Unreacted H2, okay, will remain once this reaction is complete. So we refer to Cl2 as a limiting reactant and H2 as the excess reactant. Okay. So here I have a figure shown where we're looking at Cl2, which are green spheres here, and then H2, which are the white. So I have 6 H2 molecules and 4 moles or 4 molecules of Cl2. And then after the reaction, I have 8 molecules of HCl, which are the green and the white. And I have 2 molecules of H2. So this is my excess reagent. So here, this is just a picture showing you, instead of we're talking about moles, we're talking the coefficients can also represent the molecules, number of molecules in the chemical reaction reacting together. And so here we're seeing that we have excess H2, okay, and that our limiting reactant would be our Cl2. Okay, so that brings us to example 4.12. So here we're given a balanced chemical equation. They say silicon nitride is very hard, high temperature resistant ceramic used as a component of turbine blades in jet engines. It is paired according to the following equation, which is the limiting reactant when we're starting out with 2 grams of silicon and 1.5 grams of N2. So here's my information here. So the strategy here is I need to go ahead and convert everything to, we can stop at moles or grams, doesn't matter. I'm going to do it the easier way and stop at moles because it's a little bit easier to stop at moles and stop at grams. Okay, so the strategy is here to convert moles of silicon to, we're starting out with grams. Grams or mass of silicon to moles of Si3 and 4. Okay, I'm going to do the same process with the next reactant. So the mass in grams for N2, I'm going to convert that to moles of Si3 and 4. And same strategy here. The least amount is going to tell me what my limiting reactant happens to be. Alright, so here for silicon, I'm starting out with 2 grams of silicon. So write my given information over 1. Okay, so I need to go from grams of silicon to moles of silicon using molar mass. Alright, so that's not too bad because it's just one element there. So I looked up the average molar mass for silicon. And so 1 times 28.09, which is 28.09 grams per mole. Okay. Alright, so 28.09 grams of silicon is equal to 1 mole of silicon. Alright, so now I went from grams to moles, so I need to go from moles of silicon to moles of Si3 and 4. So using my molar ratio here. So for every 3 moles of silicon, so I have moles of silicon here, I need moles of silicon down there, so 3 moles of silicon, I can produce 1 mole of Si3 and 4. Okay, that. Alright, so 2 times 1 times 1, that's 2 over 1 times 28.09 times 3, and that is 84.27. 84.27, and that is 0 to 3. And see, I'm starting out with 2 sig figs here, so that's going to be 0 to 7, so 4, and that's moles of Si3 and 4. Alright, so I need to do the same process again, starting with the other reactant N2, converting mass of N2, moles of N2, moles of N2 to moles of Si3 and 4, and then see what I get. Okay, so this was for Si, and so now I'm doing for N2. So I'm starting out with 1.5 grams of N2. That's what I was given here. So 1.5 grams of N2. Okay, so I need to go from grams of N2 to moles of N2. So N2, so there's 2 times 14, so that's 28 grams per mole. Alright, so 28 grams of N2 is equal to 1 mole of N2. Alright, now moles of N2 to moles of Si3 and 4, so I have to look at my chemical equation here. So I have 2 moles of N2 will make 1 mole of Si3 and 4. So 2 moles of N2 make 1 mole of Si3 and 4. Okay, so now my units cancel out here. So 1.5 times 1 times 1 is 1.5 over 1 times 28 times 2, and that's 56. And so when I do the math, I get 0.0268 and change. And so I started out with 3 sig figs there, so it's going to be 0.0268 moles of Si3 and 2 and 4. Alright, so now I'm just comparing these two anyways, right? So 0.024 versus 0.026. So obviously I can make more Si3 and 4 with the N2 that I started out with. So my limiting reactant is going to be silicon, because this is the least amount I can make. Okay, so the question of what is the limiting reactant here, and that's going to be silicon. Alright, so this is something that you've actually had experience doing before in the lab, and that's calculating percent yield. Okay, so we need to understand a couple of key concepts first before we actually try to do some calculations. So there's a difference between a theoretical and an actual yield. Okay, so what are those two differences? So the amount of a product that can be produced by a reaction as calculated by the stoichiometry of a balanced chemical reaction is called the theoretical yield of the reaction. Okay, so basically anytime you're calculating something on paper, you're basically, and you're starting out with a balanced chemical reaction and not experimental values, then that's going to give you a theoretical yield. Now, the amount of product obtained is called the actual yield, and it's often less than the theoretical yield for a number of reasons. So actual yield is actually what you get out of the experiment. So it can also involve calculations. A lot of times, you're going to take, you're going to do difference calculations, for example, whenever you're trying to determine mass, if you're having to figure out, for example, the mass of a substance, and you have the mass of what the beaker is and all of that stuff. So those technically are still calculations, but basically actual yield is what you actually get out of your experiment. For example, if you synthesize something, you're measuring the mass of copper, for example, at the end of the experiment. That is your actual yield. Okay, so they're saying that theoretical yield and actual yield aren't always, they're usually not the same. And there are different reasons for that. Sometimes you have competing side reactions. For example, all the reactants we get are very pure, but they're not 100% pure usually. So you're going to have side reactions. You can have other compounds in there reacting with your reactant there and eating up some of your reactant amounts. An incomplete reaction, okay, and that can happen for different reasons. Maybe you didn't mix up the reaction. Maybe you have some droplets on the top part of your beaker that's not getting down to where the other reactants are, and they're not able to react together. Being able to recover the product every time you switch glassware. If you're pouring your solution into another beaker, you're going to lose some of that solution. It's not going to be 100%. It's not going to be transferred to the other beaker, and so that's another way you can lose product. You can spill some of it if it's a solid. Sometimes you're weighing it out, and it's very, if it's very dry, it can hop out of the little dish that they're using. So there are a lot of different reasons why the actual yield and theoretical yield are usually not the same value. So when we're trying to calculate percent yield, like you did the other day, it's going to be the actual yield divided by the theoretical yield times 100%. What you actually got from the experiment divided by what you calculated you should get times 100. So when calculating the percent yield, both yields must be expressed using the same units, so the units will cancel. So percent yield is just basically a percentage. It doesn't have a unit. It's just a percentage value. All right, so here's our first example. We're starting out with a reaction of 1.274 grams of copper sulfate with excess zinc metal. All right, so what they're saying here is that we're starting out with a certain mass of copper. We have more than enough zinc. It's in excess. Okay, so you don't have to worry about knowing how much zinc you have. And then 0.392 grams of copper metal was obtained, okay, as a product according to the equation. So the question is, what is the percent yield? All right, so here we have our balanced equation, and we are asked to calculating the percent yield. So we know the percent yield is the actual divided by theoretical times 100. And they also give us some certain values here. They give us 1.274 grams of copper sulfate. So 1.274 grams of copper sulfate. And then we know that we have 0.392 grams of copper metal that was obtained according to the equation. All right, so we had to basically figure out theoretically how much copper was obtained. Okay, so this value they give here is the actual copper metal that was found. All right, so we actually have, this is actual, this is what we found here. So basically that's going to go, the top part, 0.392 grams of copper was found. Now we need to find our theoretical value. Okay, so if we're starting out with 1.274 grams of copper sulfate, we need to convert mass of copper sulfate to moles of copper. Okay, moles of copper to mass of copper to find our theoretical value. Right? So here we need to find the molar mass of copper sulfate. All right, so let me get another piece of paper here. So copper sulfate. So there's one atom of copper. Its molar mass is roughly 64. And 63.55. I'll just put it like that. 63.55. For sulfur, there's one atom of it. It is 32.07. 32.07. And then for oxygen, there's 4 atoms of it. 16. 64. Alright, so adding everything together, and I get 159.62 grams per mole. Alright, so here I have 159.62 grams for every 1 mole, and we're talking about copper sulfate here. Copper sulfate. Okay. So now I have grams of copper sulfate. I'm left with moles of copper sulfate. Now I need to go from moles of copper sulfate to moles of copper. Notice it's a 1-to-1 ratio, so that's easy enough. So 1 mole of copper sulfate will produce 1 mole of copper. Alright, so here I'm taking 1.274 times 1 times 1, which is 1.274, over 1 times 159.62 times 1. And so then I do the division there. And what do I get here? I get a very small number, 0.00798. Okay, and that's moles. Oh, that's moles of copper. And I need to do one more conversion. So I need mass. That is a tiny number. Okay, so I need to do one more problem, one more step here. So I have 0.00798 moles of copper. And I just didn't realize that. I need to do one more step. There we go. Okay, so for every 1 mole of copper, it's so many grams. I have to look that up on a periodic table. And that is 63.55 grams. Alright, so I multiply that times 63.55. And then I get 0.507 grams of copper. Okay, so probably can add a number to that. So 2. There we go. So 4 sig figs there. Started out with 4. Alright, so now that is this. So this is my theoretical. right? Theoretical value. So going back to my percent yield here, I added my actual value, which they gave to us, and I had to calculate my theoretical. When I did that, I got the 0.572. So 0.5072 grams of copper. All right, so now I have to just do the calculation there to get my percentage. 2 times 100. And I get 77.28 or 29%. All right, so that's what I get for my percent yield.